Hello everyone, welcome to the channel. So today we'll be studying circuit analysis with the help of Kirchhoff's law. So there are two theorems. The first one is loop analysis theorem. The second one is node analysis theorem. So let's get started. Loop analysis theorem. Now this theorem is based on Kirchhoff's voltage law. Let's assume this electric circuit. It has an electric source E, impedance Z1, Z2, Z3, Z4 and Z5 present in it. Current I1 is flowing through loop 1, current I2 is flowing through loop 2, and I3 current is flowing through loop 3. And we are traveling in clockwise direction in loop 1, loop 2, and loop 3. Now let's apply Kirchhoff's voltage law in loop 1. Now current I1 is flowing through impedance Z1 and it is in the same direction as we are traveling in the clockwise direction, so it will be positive Z1 I1. Now as for impedance Z3, I1 minus I2 is current flowing through it and it is in the same direction as we are traveling. So it will be positive Z3 I1 minus I2. As for electric source, we are traveling from lower potential to higher potential, that is from negative to positive. So it will be minus E is equals to 0. Now we will take common out, so we will get this equation. Now we will apply Kirchhoff's voltage law in loop 2. So current I2 is flowing through impedance Z2 and it is in the same direction as we are traveling. So it will be positive Z2 I2. The same goes for the impedance Z4. I2 minus I3 current is flowing through it and it is in the clockwise direction. So it will be positive Z4 I2 minus I3. As for the impedance Z3, I1 minus I2 current is flowing through it and we are traveling in the opposite direction to the current. So it will be negative Z3 I1 minus I2 is equals to 0. Now we will take common out and we will get this equation. Now we will apply Kirchhoff's voltage law in loop 3. Through Z5 impedance, I3 current is flowing, so it will be positive Z5 I3. As for the impedance Z4, I2 minus I3 current is flowing through it and it is in the opposite direction as we are traveling. So it will be minus Z4 I2 minus I3 is equals to 0. We will take common out and we will get this equation. Now equation 1, equation 2 and equation 3 in matrix form can be written as shown here. Now Z will be the matrix of impedance, I will be the matrix of current, and E will be the matrix of voltage. Now what we are doing here is that we are using loop analysis theorem to find current in all the branches of the electric circuit. So what we will do is that we will take matrix of impedance and we will find determinant of it. After finding determinant, what we are going to do is that we are going to replace the matrix of voltage into the first column of the matrix of impedance and we are going to find determinant of that. After that, we are going to replace the matrix of voltage into matrix of impedance in the second column and we are going to find determinant of that will be the second determinant. As for the third determinant, we are going to replace matrix of voltage into the third column of the matrix of impedance. Now current I1 will be given by first determinant by determinant of matrix of impedance. Current I2 will be given by second determinant by determinant of matrix of impedance. And the third current will be given by third determinant by matrix of determinant of impedance. In the general form, we can write is as shown here. Now this is the loop analysis theorem. Node analysis theorem. This theorem is based on Kirchhoff's current law, and in this theorem we are going to use admittance in place of impedance. Admittance. Admittance is basically the inverse of impedance. It is denoted by y is equals to 1 upon impedance. Now from Ohm's law, V is equals to Iz, where Z is the impedance, I is equals to Vy, where Y is the admittance. Ohm's law in admittance form. Now, what we are going to do in node analysis theorem is that we have electric source E, admittance Y1, Y2, Y3, Y4, and Y5. We are going to apply KCL at node A and node B and find the electric potential. After that, we are going to apply Ohm's law in admittance form to find the current in every branch of the electric circuit. Now, with the help of Ohm's admittance form, we can find the current in all the branches of the electric circuit. Since current I1 is flowing from potential E to EA through admittance Y1, I1 will be equals to E minus EA into admittance Y1. Current I2 is flowing from potential EA to EB through admittance Y2. So current I2 is equals to EA minus EB into admittance Y2. Now let's say this is point C and this is point D, and since this is electric source E, electric potential at C will be equals to E and electric potential at D is equals to 0. And since it's ideal wire and this is point E, the potential at E will be also equals to 0. The same goes for the point F. Electric potential F is equals to 0 since this is also an ideal wire. And this is point Z and this is an ideal wire. So potential at Z is equals to 0. So from that we get I3 is equals to EA minus 0 since we are traveling from potential EA to 0 potential to admittance Y3, EA minus 0 into admittance Y3. As for the current I4, it is traveling from potential EB to 0 potential to admittance Y4. We get I4 is equals to EB minus 0 into admittance Y4. And I5 is equals to EB minus 0 into admittance Y5. Now we are going to apply Kirchhoff's current law at point A. Since current I1 is flowing toward point A, current I2 is flowing away from point A and I3 is also flowing away from point A. So I1 minus I2 minus I3 is equals to 0. We will replace the values of I1, I2 and I3 and we will get this equation. We will take EA and EB common out, we will get this equation. Now we will apply Kirchhoff's current law at point B. At point B, I2 is flowing towards the junction, I5 is flowing away from the junction, and I4 is also flowing away from the junction. So we will get I2 minus I4 minus I5 is equals to 0. We will replace the values and we will get this equation. And from first and the second equation, we can find EA and EB, and we will replace those values here and we will find the current. So that's all about node analysis theorem. Thank you and have a nice day.